Yeah, we start with this example of LC circuit theorem. It's a simple problem to start with. We have a coil of 0.12 Henry and a resistor of 4 ohms present, and we have a voltage source of 240 volts. So in this case, the 240 volts there is the RMS value. Please bear that in mind since it was not stated. And the first thing to do is to calculate the reactance. As you can see here, the inductive reactance. The circuit consists of an inductor of 12 Henry, 0.12 Henry rather. So what we need to do is to calculate the impedance, which is X subscript L, this one, and then that gives us this value using the formula for reactance. For the impedance, we already know that since it is a resistance and inductor circuit, no capacitance, so there will be no capacitor, so there will be no capacitive reactance. So we only have a resistor and an inductor to give us this result. Having known the impedance Z from the reactance of the inductor and the resistor stance of the resistor, we can then proceed to calculate the current. The current here you can see, though it's not stated with subscripts carrying effective or RMS, but it is the RMS current in this problem. Please bear that in mind. So we move on now to second example. In this second example, we have a question there, a PD of 20 volts RMS value, then a PD of 20 volts RMS value. So we also have there the frequency of about 1000 Hz, as you can see there. Alright, so from the values of the frequency, we can determine the capacitive reactance since it's a circuit that consists of a capacitor and a resistor. So in this very question, we have the capacitive reactance as this. Please take note of that. So that is the capacitive reactance there. So we apply the impedance for the circuit involving a capacitor and an inductor. So we arrive at this value for the inductor. Please do well to follow the calculation. Yes. Then we take the law for Ohm's law for the impedance circuit. Ohm's law generally we know is V is equal to IR, where I is the current, R is the resistance, V is the voltage. So for this AC circuit theorem that involve a capacitive reactance and a pure resistor, the arrow there is there for the impedance Z. So that is the Ohm's law statement. So the current can now be expressed as V over what R, which is Z, and we arrive at a good value here. But they told us that we should also, number three, that we also need to calculate the voltage across the resistor alone. Because it's a series connection, we know that the current through the capacitor and the resistor will be the same. That's so the same current that we calculated that time, which is this one, will flow through the capacitor and the resistance. So applying Ohm's law to the resistor alone, that will give us V is equal to IR. So the voltage V here represent the voltage across the resistor alone times the constant current. So this is the current that we calculated and the resistor value of 100 ohms that we know. So this gives us the voltage across the resistor alone. Please take note of that. So now we turn from there to the next one, the phase angle. The phase angle is the angle between the voltage of the voltage of the source, the angle between source voltage and that across a resistor, or simply the ratio of the impedance of the capacitor to that of the resistor. So the phase angle also tells us by how much uh, the voltage leads the current in the circuit. So in this circuit with capacitive resistive circuit, the voltage actually does not lead the current. The current leads the voltage, or rather the voltage lags the current here actually. So this is the phase angle. The angle is about 4.52 degrees. Follow the simple mathematics there by taking the arctan of both of the other side, the right hand side. After imputing the values of 7.9 for the impaired reactance and 100 for the resistor, all values are already present here. 100 resistor, the reactance we have calculated to be this value. Yeah, I've seen it before. All right, that gives us the result for that one. So example 3 is very simple, another series connection, and in this very connection we can see that it's very problem rather, we can see a resistor, an inductor and a capacitor, three circuit elements. So this time the impedance is going to consist of a resistance, and capacitive reactance and inductive reactance will be present all together. So we have to compute all three before we can calculate the impedance for the circuit. So we go this way. If we do that, we arrive at the voltage here. VRMS value for the voltage is this. We use the formula for the RMS value relating to the value for the voltage peak value. That will give us the result we want. As we know before now, this is the VRMS value is equal to the peak voltage times 1 over root 2. That 1 over root 2 is 0.7071. The peak voltage is 240. From here, because the instantaneous voltage V is given by 240 sine 1000 t. Okay, 1000 t, please, there's a t here. That means angular frequency is 1000, so which is 1000 rad per second. Please take note, angular frequency is not exactly the same as frequency. It is 2 pi times frequency that will give you the angular frequency. So the angular frequency is measured in rad per second, while the frequency normally is per second, which is in hertz, also known as hertz. So this is 2 pi f equal to 1000. So since we know W, no need for us to go and find f because it was not required. Now we calculate f. All we need to do is to apply W into the direct formula. Omega c, 1 over omega c gives us the reactance and the capacitance, and that will give us this value. As you can see here, I think it should be 100. Should be 100. So I've calculated the impedance for the before we calculate impedance, we need to know the reactances using their respective formulas. This is for capacitor, this is for the inductor, omega L, where L is the inductance, and here C is the capacitance. Omega here is already 1000 as we can see. So we now proceed to calculate the impedance, and the impedance is this way. The formula you are seeing, it is a reactance minus the capacitive reactance. So the circuit impedance for the inductor minus impedance of the capacitor, all squared. That has been done here. There the resistor is also squared, and in the end we arrive at this number, and then we go on to solve number 3 Roman figure. That's the current flow in the circuit is the RMS value over the impedance found. That will give us this current. Then the phase angle is the impedance of the inductor minus the impedance of the capacitor over the resistance. And this, if the impedance is positive, if the phase angle is positive, it means that the inductive reactance is greater than the capacitive reactance. That tells us that the voltage is ahead of the current in this very problem. So by some angles, all right, by some degrees, as we can see. So that is that. And the power dissipated is the energy spent in the circuit in form of heat. That energy is usually expended in the resistor, not the capacitor, because the capacitor and the inductors, they are not pure resistance. So the only pure resistance is that provides the only component that provides pure resistance is the resistor. So therefore, the energy expended or spent in the circuit is the power, and we can calculate the power in this manner as you can. So we can see that is the power I square R from Ohm's law. So the power is the square of the current times the resistance in the circuit. Okay, as you can see there, so much for the circuit. And here are some exercises, a very few number. We also have many questions under this topic, but try these ones out. In subsequent times, you come across more questions. So have a good time out doing this. Bye for now.